Today I'll be presenting the paper, A Data-Driven Motion Prior for Continuous Time Trajectory Estimation on SE3 for ICRA 2020. Let's get started with some background. Simultaneous Trajectory Estimation and Mapping, also known as STEAM, is a framework for continuous time trajectory estimation, where the trajectory is represented as a Gaussian process. Continuous time estimation has been used in the past, and its benefits have been widely discussed. I won't go into the details, but in summary, there are cases when a discrete time framework is inadequate. Some examples include when using high-rate asynchronous sensors or continuous scanning while moving sensors, such as scanning laser rangefinders or rolling shutter cameras, where the pixels in a frame are not all exposed at the same time instant. This effect is demonstrated when taking a picture of a propeller rotating at a high speed. In a continuous time estimation framework, measurements can be incorporated at any time without introducing additional states at those measurement times or making ad hoc assumptions about smoothness. I also wanted to provide a high-level overview of what is involved in the STEAM framework, which estimates a continuous time trajectory as mentioned. There are two inputs to the system, sensor measurements, and a Gaussian process motion prior, which is the key for achieving continuous time estimation. This motion prior encodes some information about the smoothness of robot trajectories, which is highly dependent on the robot itself. There have only been two priors used in continuous time estimation in the past, white noise on acceleration and white noise on jerk, where either the acceleration or jerk is modeled as a white noise process. Our research will focus on how to improve this motion prior. So let's dig into the details of this a bit more. To exploit sparsity for efficient computations, our motion prior must be in the form of a linear time invariant stochastic differential equation driven by white noise, as seen in the equation below. Wt is the white noise process with pyrospectral density Qc, a hyperparameter of the prior. The state and system matrices are shown for the white noise on acceleration and white noise on jerk priors below, where the B matrix is 0 for both priors. Because our states are in SE3, we can't directly apply these motion priors to our estimation problem. However, Anderson et al. Define a set of local state variables that are in vector space, where we can form a set of locally linear priors between two states at consecutive time steps. For more detail, see the papers by Anderson et al. And Tang et al. It was previously shown that the white noise on jerk prior could be formulated so that its mean matches the mean of any white noise on acceleration prior. However, the covariances can never match. In the figure below, where we sampled many trajectories of each prior, you can see that despite the mean being the same, the covariance of the white noise and jerk prior grows at a much faster rate than the white noise and acceleration. This leads us to the question, how do we know what our motion prior should be, or how to pick values for the hyperparameters? We will seek to answer this in our work. With data-driven modeling methods becoming very popular, we wondered if we could do something similar with the motion prior. We could use a richer motion prior and learn its parameters from data. While deep neural networks have become very popular as a universal function approximator, we want to use something where we can still retain the linear time invariant stochastic differential equation form mentioned previously. This allows us to exploit sparsity for efficient computations and also allows us to take advantage of Gaussian process interpolation for continuous time estimation. In addition, GPs also provide a well-understood way to propagate uncertainty. We investigate the use of latent-force models, which provide a way to combine mechanistic, physics-based models such as stochastic differential equations with data-driven models. In latent force models, usually an overly simplistic mechanistic model is augmented with latent forces represented as a Gaussian process. Therefore, the GP must be rich enough to model interactions not captured by the mechanistic model. For example, in the white noise on acceleration case, latent accelerations are represented by a white noise process. We argue that this is not sufficient for representing many robot trajectories. In our method, we choose to represent latent accelerations that the robot undergoes as a Gaussian process with a Matern covariance function, or kernel function. This is a family of covariance functions commonly used in Gaussian process regression. We set the parameter nu to 1/2, which results in this covariance function. Here we can see that there are two hyperparameters, variance and length scale. However, we still need to be able to get this into the form of motion priors we are interested in. We can actually convert this GP into a stochastic differential equation driven by white noise, where the parameters alpha and QC are parameterized by the length scale and variance. From here, we can augment the states to include position and velocity, which gives us a linear time invariant stochastic differential equation, which is what we want. The system matrices are shown with the B matrix as 0. This particular parameterization of our motion prior actually collapses into the Singer acceleration model. It turns out that our formulation of the Singer acceleration model can represent both white noise on acceleration and white noise on jerk trajectories, but is not limited to those two types of priors. On the figure on the right, we can see that certain parameter values for the Singer prior can make it act like either a white noise on acceleration or white noise on jerk prior. This is achieved by modifying alpha, our parameter that encodes the length scale. We also provide some more details in the paper, which we won't discuss in this video. This includes deriving the error terms and covariances for the Singer prior, which are needed to incorporate it into the cost function. Hyperparameter training with noisy measurements is quite common in vector space, but we also show how to train hyperparameters with noisy ground truth when our state is in SE3. Now moving on to our experimental setup. It consists of a vehicle with a Velodyne 128 Lidar and an Applanix pause LV positioning system for ground truth. The dataset that we collected consists of two routes. On one route, we used the collected ground truth for training the hyperparameters for each of the three priors, white noise on acceleration, white noise and jerk, and the Singer prior. The other route is our test route, which we will use to test Lidar Localization and Lidar Odometry. After training the hyperparameters of each motion prior, we run our Lidar Localization test procedure, which involves collecting data from two runs of the test route. In the first run, we use the data to create a LiDAR map of the area using a tool from Applanix Corporation, the provider of our pause ground truth system. On the second run, we collect LiDAR data and ground truth. We use the LiDAR data to localize against the map created from run 1 using an Applanix LiDAR localization pipeline. This pipeline produces pose measurements with covariances, which we use in our STEAM framework, along with one of the trained motion pairs. This produces a continuous time trajectory estimate, which we can then query at the ground truth time steps to compare with our ground truth. We run the same estimation problem for the white noise on acceleration, white noise on jerk, and Singer prior for comparison. Here are some results of our LiDAR localization experiment. This graph shows the translational and longitudinal velocity errors for each of the priors when we have measurements at 10 Hz, or every 0.1 seconds. The exact same estimation problem, but with the Singer prior, is able to reduce both errors as compared to with the white noise on acceleration and white noise on jerk priors. Because we have pretty accurate LiDAR localization pose measurements, we increase the difficulty of our test by increasing the time between measurements from 0.1 seconds all the way up to 5 seconds. Even in these tough conditions, we see that the Singer prior is still able to do better than the two previous priors, which begin to perform poorly. Here are some qualitative observations from our experiments from our tests with the 4-second measurement dropout. In the figure on the left, we overlay a portion of the trajectory estimate with dashed lines showing the point at which the estimates would actually deviate from the lane boundaries on the road. We see that the estimate with the Singer prior always stays within the boundary, whereas the same cannot be said of the white noise on acceleration and white noise on jerk prior. The figure on the right shows the longitudinal velocities plotted along with the ground truth. We see that the Singer prior is able to better capture peaks in the longitudinal velocity. These peaks correspond to changes in acceleration, which occur frequently in a moving car. The second experiment that we perform is using the three motion priors within a LiDAR-only odometry framework, which was used in some previous papers. We see that the Singer prior is once again able to improve our state estimates compared to the two previous priors. Also, looking at the trajectory plotted against the ground truth for one of our test sequences, we can see that the Singer prior noticeably reduces drift in the Z direction. In conclusion, we have developed a method to train hyperparameters of motion priors in SE3 using noisy ground truth. We then introduce a richer motion prior and apply our training method. We show on two estimation problems that using this new motion prior outperforms the previous white noise on acceleration and white noise on jerk motion priors, each of them trained with data. In this work, when training parameters of our motion priors, we assume that we have noisy ground truth, that is, we have measurements of the entire state. However, parameters can still be learned without ground truth, using only measurements from whatever sensors are available. We show how to do this in the following paper cited below. Thanks for listening.